So I am going to be talking about parallel and concurrent programming. And I titled this talk, Dear God, What Am I Doing? Because that's what it felt like for me when I just started. So if you've ever felt like that, this talk is for you. So if you are scared of these things, like when you type them, how many people have used these things when they program? Okay, most people. So that's good. Actually, I gave this same talk last week at RubyConf Australia, and a lot of people had already had experience with them, so I've actually changed the talk to go faster over some of the basics and get into some more advanced stuff. And I also wanted to, I named the talk how it was just so I could show this picture. Yeah, because the first time I actually did some work like this, I totally messed up and it was just embarrassing. And the dog sums up how I felt when I was programming, but I was getting paid for that, so it's cool. So the brief introduction to the things we're going to be using, pretty much computers are the most complex thing humans have ever made. And we can actually break this down into a very simple diagram. So here we have a hamster on a wheel, and okay, Keynote is really slow with GIFs, but there is a hamster which is like a thread, and the wheel is like a process. The wheel is like a process. So we have processes which are composed of threads, and the kernel runs our processes. So when we want things to go faster, we would just think, okay, I can take what I have now and just do multiple things, or just do that like all over the place. So we go from one wheel to this. And we magically, like our code just runs faster, and we do like n number of things at once, and it's just magical. But like in reality, what happens is we mess up, and when we fall off the wheel. Like, that was me. I had a thread in the instance variable, and I used that to kill something. And if you kill nil, yeah, you can really blow up your computer. So, like, the whole point of this talk is how can we make our programs faster? And generally, the answer to that is we can make them do more things at once. So I am a car guy, and this is a turbo. And a turbo works by compressing more air and shoving that into the engine to make a more powerful explosion. And when I make my programs go faster, like this is what I think about. Like how can I feel more acceleration? How can I feel more power? So just do multiple things at once. So we have three primitives. We have processes and threads. And also Ruby gives us fibers. So I mentioned earlier that a process is composed of threads. The kernel decides when to run threads. Threads can block for various reasons, mostly I/O. And fibers are like threads, except that you have control over when a fiber executes. So you can start and stop a fiber. You can also kind of start and stop threads, but it's not exactly the same. And you can make new processes by process.new or fork. So the most important thing to take away in the very beginning is that the kernel is deciding what is going to run your code. So it's going to schedule your threads and schedule your processes. And I/O will usually make those things block. So quick introduction is that we have things behave differently on each interpreter. And prior to Ruby 1.9, giving this talk on MRI is just essentially a huge troll. Because in 1.8, there's green threads. So now in 1.9, every thread is actually backed by a native thread, and multiple things could be happening at once. And that's not the case with Ruby 1.8. And then this is also different in MRI and JRuby, and also in Rubinius. So the easiest way to get started is just by using threads. So you can make a new thread just by simply calling thread.new, and then it will run and do stuff. But if this was your only code in the program, there would be a problem. Who knows what the problem is? Exactly, you don't join. Because once you start introducing parallel like execution paths in your code, you have to keep track of them. So in this case, if you just start this, the main thread is going to exit right away after thread.new is called and thread.new. The hello world will never come to the screen. So what you have to do is join your threads. And this is essentially just waiting for all your threads to finish. So the main thread will wait, and you'll see hello on the screen. And you'd see something like this. And if you run it again, it will be different. So you don't have control over when your thread's executing, the kernel's doing it for you. So if you're trying to do order-dependent code, you're going to have a bad time. And threads also share the same memory space. So like in this example, both parts of the code can use the balance and change it, which maybe you don't want. So now we're at a situation where we can have two pieces of code executing and need access to global state. And obviously we can't have two people like withdrawing or working with the bank account at the same time. So in order to fix this problem, we have to make the code path exclusive. And to do that, we introduce a lock. And the Ruby Center library gives you a simple mutex you can use. So you can wrap parts of code and synchronize to ensure that only one Ruby thread can be in that block at the same time.
What is the magic number?
Magic number?
1 point.
Oh, it was just, okay, so that was just an example of one thread can be changing the balance, and you can see it in the main thread. I actually forgot to include the output slide, so there you go. So, and we have blocking. So like in these examples, nothing is ever going to block because it's just Ruby code. However, the second you do like network access or any type of I/O, then the thread is going to block and the kernel will select a different thread to run. So if you heard of Node, and it has non-blocking I/O, which is essentially the opposite, and apparently it's pretty cool. So essentially, I/O is the thing that's going to block most of the time. So that's the rough overview of threads, and now we're going to talk about processes. And you introduce a process by usually just using fork. And here is like the same example where we fork off one thread that just changes the balance, and and the parent thread prints out the balance. So the difference between threads and processes is now how you deal with the memory space. So in processes, the memory is not shared. So if we were to run this code before, in the third example, the balance would be the same, whereas in this case, it's not. So when you fork a thread, a new memory space is allocated for that thread with all the references to variables. Yes, in the back.
You didn't mention about non-blocking I/O.
Yes, I didn't.
Why?
Because I didn't want to, actually. I just didn't want to talk about it. Because I think that there is non-blocking I/O is something that you can achieve by using like evented or event machine or celluloid I/O, which I mentioned later. But in the talk, I wanted to focus more on simply how you can construct multi-threaded or multi-process programs.
Why?
Because
You know, okay, I understand that some kind of problem with non-blocking I/O. You mentioned that even machine.
sorry?
I suspect that is some kind of problem with non-blocking I/O in Ruby, yeah?
Well,
You mentioned even machine.
yeah, if you
That you prefer multiprocess and instead of multithreaded, yeah? With non-blocking I/O, for example.
no, not really. I prefer multi-threaded, not multi-process.
Why you didn't mention about non-blocking I/O? Okay. Till the end of the doc. Sorry. Thanks.
Okay. Okay, so then, yeah. So fibers are also important, but I think you can do more with threads and processes than you can do with fibers. So I just give a brief introduction to what fibers are, and you can use them. They're basically like threads. You can make a new one. You can call start and stop and pause it. So it gives you a primitive to create concurrent programs. So making things faster. So this is just, I'll go through a few examples of having a problem and parallelizing it. So the examples I'm going to use is how to fetch like the first n number of Google searches as fast as possible. So there's two approaches, multithreaded or multiprocess. So the first thing I will talk about is multithreaded. And before you have any experience working with threads or processes, you probably just write a simple loop like this. And it works, but it's definitely not as fast as it could possibly be. So you have cores. Your computer can be doing multiple things at once. So you can break this up to use multiple threads. So you can create a queue and then multiple threads. So in this example, I just create 4 threads and a queue. So I have 4 threads working at once and split the work up like that. And this is, what?
Why 4?
Because it's faster.
Why not 100?
Well, I will get there. Because that's the next thing. So the first thing is you think, okay, I can just split this up and I can make 100 threads, right? Or I can make 1,000,000 threads, whatever. Or if my computer is great, I can do that. So I have a single thread. It takes like a long time. Multi-threaded is significantly faster, so you think, okay, time for more threads. So I write just a simple script that you can pass in a number, like a worker number, right? And then I thought, okay, great, I'm going to get these results so fucking fast, it's going to be amazing. Like I'm on a wired connection, like everything's great. But it doesn't work. It actually gets slower. The more threads you use, it becomes slower. Because you have context switching. Like, first of all, there's a few different things going on here, but like really context switching, because the kernel is deciding like what's going on, and if the thread is not really even active for so long, say the thread is like active for maybe like a millisecond, and switching takes like a nanosecond, but if you have 1,000,000 threads, you spend more time switching than you do processing. So there is a balance, and you have to play with that to find out what's right for like your application or specific problem. So another example of this is just like brute forcing code. So like I talked with some people last night about Bitcoin mining, and Bitcoin mining basically works by computing hashes. And it's basically brute forcing. It's just like how you would crack passwords. So you write some code, you decide you want to use some threads to calculate all the different hashes. Say you have 1,000,000 hashes, you split that up into a certain number of threads, say 5, and divide it by 5. That will be pretty fast. So you get yourself like a huge computer that you can just use, and you get ready to run this thing. And it's slow, because unfortunately, there's a big problem with MRI, and that is the global interpreter lock. And in that previous example, we're not doing anything else besides executing Ruby. And the global interpreter lock ensures that only one thread can be executing Ruby code at the same time. So that like last example is essentially a huge troll, because like you think it will be working, but it's not. And that's why the other interpreters are are important when you want to do this sort of stuff. So the primary other interpreters are JRuby and Rubinius, and they both do not have a global interpreter lock. So basically, if you want to be doing like true concurrent programming in Ruby, you can't use MRI. That's just the facts. So I also like cars, and I like this meme, but I also like the JVM. And so JRuby, this is Charles Nutter, and he's in charge of JRuby, and JRuby runs in the JVM. There's no GLIL. So the TLDR is if you want to write multi-threaded programs with Ruby, you shouldn't be using MRI. So multiprocess. Now this is the other caveat, is yes, multiprocess is definitely a good way to solve certain problems. However, not every platform has them. So if you're on JRuby, or of course, if you happen to be programming on Windows, God help you, I don't know why, but you can't fork. So we can essentially like copy the same code and replace thread.new with fork. And just do the same thing. The only difference is that instead of calling join, now we have to wait on all of the child processes. And when you're working with multiprocesses, you have to deal with inter-process communication, which luckily this example doesn't have the need to do any communication. The only communication is passing a block variable into fork. So this actually is like it performs about as well as just using multi-threads. However, we know that processes are composed of threads, so what we can do is we can fork off a number of processes, and then inside those processes create any number of threads. So we can fork off four processes and then 4 threads inside that. So this is an example of just doing that. Basically take the forking code and the threading code and just put it all together. And it's the fastest. But there's really nothing else to say besides simply it is the fastest way to do like this particular thing, because you can fork off any number of processes and then fork off any number of threads. But there is a subtle problem actually in this code. Anybody who's used the Ruby standard library Q implementation may have noticed it. But you might not see this problem working with a small data set, like a small number of things. Like in our example, we're only working with like 100 pages, right? But say we want to do 1,000,000. And that's actually how I found this problem out. I tried to run the hashing example with like 1,000,000 hashes, and I had a problem. So generally, this code just happens to work. And there's a very slight problem with it, that we wait while the queue has some stuff. Okay, that's great. And then we go in the loop, and we get something from the queue. Except for empty is non-blocking. Now, that means it will just return instantly after it's called, whereas pop is blocking. So pop will wait for something to be in the queue to pop off. So occasionally, this code can deadlock because the call to empty will return true. You'll go in the loop, and the queue is now empty, and nothing is going to populate it again, and it's sitting there waiting to pop off, and you'll get a wonderful deadlock error. So deadlock is basically a situation that cannot be resolved, and it just blows up. So the simple fix for this is to wrap that whole operation of checking the loop condition and getting one thing inside a lock. So in this case, acquire a lock, and then if the queue is empty, just return false, and if not, pop and get something back. So that's just this is just a simple example of trying to do some multi-threaded stuff, and you can shoot yourself in the foot if you don't do that. And you have to actually pay more attention to the code that you're using to ensure that it's working the way it is, because that actually is not documented in the queue class. It only states that the pop is blocking. Yeah.
Are you extending the array with that method?
Yeah. So
wouldn't you get into an infinite loop by calling hop on the array, which you are already? So you recall the same method again and again, right?
No, because, okay, this is actually a snippet of the class, because this would be inside the queue class, and the queue has a internal instance of array it uses to keep track of everything. So most of us are web programmers. I mean, I am, and like we want to serve our websites faster. And well, we want to do more things at once. So I think Unicorn is very popular, and that uses like a pre-forking web server. So basically, start up a process, get to a certain point, and then fork off, you know, like 4 or 5 workers, however many your machine can handle, and now, boom, you can now handle, you know, n times whatever more requests at once. So we have a process managing them and a number of worker processes, and the parent process is keeping track of the children to make sure that they're alive, if they handled requests, is it done, whatever, so it knows which one I can send to. The second, the children and the parent are communicating over sockets because now they're multi-processes and you can't just ask how you're doing, you have to set up a communication channel. And boom, they all take memory now because you have just forked your process and that's going to give you a new memory space. So these things don't just come for free, there is a penalty that goes along with it. Yeah?
There's copy on write, and this will happen actually after first garbage collection, and it won't happen with the
Say again, sorry?
So if you fork a process, the child process doesn't automatically get the memory allocated.
Right.
There's copy on write, so if you change a bit of memory, page of memory, it will be like duplicated for the child process.
Right.
So and the problem with Ruby 1 up to 1.9, I think, was that every time you did garbage collection, that every page of your application would sort of be updated. So the child processes would take 500.
Yeah. So yeah, I'm glad you brought that up because what I'd say, okay, they all have it, but the point is, they will be forked and you'll have some additional memory. It may not be the exact same, but it comes at a cost. You do have to pay the memory for the child processes. So there's a lot of things happening inside Unicorn that make it a good example of all the it works well, but it's very complicated, and you have to worry about monitoring and inter-process communication, which are non-trivial things to do, and there is a memory cost. So there is a way to write these types of applications much easier, and I think that the answer is celluloid. How many people have used or heard of celluloid before? Okay, most people have been exposed to it through Sidekick, if you use that. So celluloid is based on the actor model. So each actor runs in its own thread, and celluloid uses a mailbox to allow you to communicate between actors. That's the rough overview, but it does a lot more. So it's written by Tony Ascieri. He's a really tough name to say, but actually he won the Ruby Hero Award last year for his work on celluloid. And you can do pools with it. It will handle supervision, like logging, prevents deadlock. It handles like essentially all the pain points you run into when you try to write programs like this. It solves them in a really nice way. So handling pain points, yeah. So in celluloid, it has a built-in facility to monitor threads. So for some reason, if your worker crashes, for whatever reason, celluloid will detect that and start it back up again. You don't have to worry about it. You can also save this, like reference to this worker for later and access it wherever you want in the code. So if you have another file, you can just say, okay, I need to push some stuff onto my like worker or my queue or whatever. So inter-process communication. Celluloid doesn't use processes, it uses threads. So that's why it's in quotes. But your workers are objects and you communicate with them by passing messages. And it gives you a mailbox to accept messages and the worker can handle those messages, can block or wait for them. So mailboxes work everywhere. If you have a reference to one, you can pull it back and just send it a message later. So here is a simple example of using a mailbox. It's just one class that waits for messages and just prints them out, right? Like this is just a trivial example, but you can use this concept to message pass between various parts of your system. So this is actually pretty cool because you can call async and delay any method call. So that will just return immediately, and you can do something else in the background. And then the receive call actually blocks until the block returns true. So you can wait for a message. And you'd see something like this. I think probably like the coolest thing is this, the way it handles pipelining to avoid deadlocking. It's scheduling method calls and all sorts of stuff like that to hopefully avoid deadlocking. According to the documentation, you should never get it to deadlock, but quite frankly, I don't believe that. But I could definitely see how it's structured. It does prevent that. So just as a simple example, going from our previous ones, we can create a pool of workers and just, hey, fetch the stuff. And it actually will, when you call worker.pool, it will create the number, like a number of threads equivalent to the number of cores on your machine. But if you want to, you can say, I want 1,000,000 threads, if you think you can handle that. So like we have code that can run in threads, and now we just want more of it. So it's time to scale out. And there is another project, part of Celluoid, that's decel, and that stands for distributed celluloid. So what you can do is you can start a worker and put it on the network. Okay? It's great. So you give it an ID, which is the node ID, and then an address, and then Celluloid uses 0MQ to communicate between all the workers. And then you can drop a cell into the node, so you can have multiple nodes, and then nodes can have many cells in them. And then in another class, you can start it up, get on the same network, and just access it. So grab a node from the network by using the node class, and then grab a cell, and then you can just send and talk to other people. And like this was just like a mind-blowing moment for me, because like I had never, it's just so easy. Like you think, okay, I have this code, now I can just put it on like 5 million machines and just talk to them, just with just simple like basic Ruby. And it's just So, and then you can also like have clusters of these things. It's just totally crazy. Like it sounds so complicated. Like you think about how you would program that and all this stuff, and somebody smarter than you has figured that out, and now you just get to use it, which is awesome. But like now it's up to you to actually do all the hard work. Like this is just like the overview. Like these are all the tools you can use to construct these type of programs. And yeah. So now I guess I will address non-blocking I/O. Yeah, so I decided not to talk about non-blocking I/O because it would require a large amount of time. And there is a way you can make your programs go faster by using non-blocking I/O. And you can, if you want to do non-blocking I/O, you can use Event Machine or celluloid I/O. And yeah, I mean, I don't know, I don't really have so much to say on it, actually.
Did you try it?
No, I haven't tried it. Because it takes a lot of setup, and you really have to like really change the way that you write the programs. And that's why I liked working with Celluloid, because it's like, oh, I just work with my objects, and now all of a sudden they're in threads, and they're all different.
This is exactly changing the way how you're working. Celluloid is just changing from normal trees to being actors. So this is same difference like event programming than normal 3D, right?
Yeah.
So,
But like when you like say for example like you're working in like a totally asynchronous system, you have to then okay now everything is callbacks, right? But like when you're working with this, you don't have to worry about that.
so you prefer actors instead of event programming, just it.
I think so, yeah, personally. Yeah.
There's also a project called EM Synchrony by Ilya Grigorich, who works for Google. So it makes your asynchronous call look synchronous.
Yeah.
So you can wrap it up in Fiber. And we are using it in production. We just write normal Ruby that acts asynchronously and just works.
Yeah, actually that's how Celluoid works too, is it wraps all the, yeah, because what you do is, because you can make the method calls synchronous or async. So actually it's like wrapping every method call into a fiber so you can start it and stop it. So, yeah. And I think you had a question or comment again.
I just wanted to mention that in Ruby you don't have to have the callback held.
Yeah, yeah, but yeah. Anybody else have any questions or comments?
Have you used decel in anything sort of real?
No, only in like cool imaginary situations. I haven't actually, like, I haven't had somebody who will pay me to use it yet.
There's also a slight problem with actor model that you don't really have shared state there, right?
Right.
So whenever you want to, you either have to keep the state like in every process or every actor that needs it.
Yeah.
Update it in every actor the same way.
Yeah.
Or you have to pass in huge messages that contain a lot of data.
Or use immutable data structures.
Yeah, but you still can't use the actor model in like single Ruby process because of the global interpreter. So
Yeah.
you communicate between processes in these cells, and then you transfer.
In a matter of fact, this is using 0MQ as transport layer, so this is exactly what you said.
I guess that's it.
Thanks, Aaron.
You're welcome.